All right, so calculus students, now you have gone a long distance enough to, now you are ready for heading into another concept in mathematics, and this concept here strictly requires that you have developed enough majority in your mathematical understanding to get here. So now here we are at looking at what it means by having or working with multivariable functions right here. All right, so needless to say that it is required that anyone arriving at this lesson to at least gone through the integral calculus in order to become mature enough. I mean, the idea to understand about multivariable functions is not hard, but it would be extremely easier for those who have been mature enough that have gone by as far as calculus with integral calculus. But now when you're taking this idea right here, it will be a lot easier. Okay, all right, so here we are at multivariable functions right here, and we're making our way into what's so-called multivariable calculus as well. Okay, so be prepared. Take my advice here before we really get into the idea right here. But anytime we're working with multivariable functions, at least from what we have already learned, we've learned and we've spent a good amount of time, and throughout all that time we've been learning about functions. And now we can just take all of your understanding. So in my advice here, take all of your understandings regarding about a function. Take all of your understanding about a function and bring those understandings of yours about functions into learning about this. Then the transition will become a much easier transition. All right, but other than that, other than giving out that advice right here, let's dive in and find out what multivariable function is all about. All right. Okay, so just a quick brief back right here. So at this point, for anyone learning in this lesson, when you arrive at this lesson right here, then you should be well familiar with something like this. So let's say v equals 5x squared plus 3x. Okay, so this is a variable. This is another variable x. So here we have an equation, and then in this equation, one variable equals an expression in terms of the other variable. But throughout the whole equation here, we have only two variables involved right here. All right, and so now in this way, in what we have learned previously, in what we have learned up to this point, we can see that v, right, is a function. All right, because in a way how I see on the right hand side right here, the reason I call this v here as a function because it's a rule, and we can treat the x here as an input. So the x right now in this equation is a variable, but once we assign different values to that variable, then the different values of the variable here determine the output's value. And so in that way we take the value for the x as the input's value. We generally call it like that. And then so the rule here, a function is a rule. The rule says we multiply the variables, the value of the inputs by, the square of the inputs by 5, and then we're going to add with 3 times the value of the inputs. Okay, so clearly v here is a function of x. And so in that way we can understand that v can be written as some function. See, we can assign the whole rule here. It's a function, it's a rule. So a rule that's taking inputs x right there. All right. So this idea is not new at all. We have an input and we put it in, we follow the rule and we come out with an output. Okay, so the value for that. And so now, and back to what I was giving out as an advice earlier, take all of that understanding as much as you can. And so from your past courses, whoever your instructor that was giving you the understanding about the function right here, bring all of that understanding. All instructors may have different interpretations of what a function is, but in the end, you guys should all be working with the same stuff like that. So now I'm going to provide the following right here. So at this point in our understanding, a function is simply a rule that takes a value that we assign for an input, and then follow the rule to come out with an output, to calculate and to come out with an output. Okay, that's the simplest way of putting it. Otherwise, it's going to take another whole course, to just relearn about what a function is. So now I'm going to come up with the following. how about I want to call that the z, where's the variable, equals now 3x squared plus 4y. All right, it's an equation. It's an equation. And then 3 times x squared plus 4 times y. So this equation of mine right here, right out of observation, right out of what we have observed, and we are looking at 3 variables. The lonely variable on the left-hand side here is equal to an expression that involves the other 2 variables. So the x and the y variables are on the opposite side, whereas the z variable is standing by itself here, pretty alone right here, by itself on the other hand, on the other left-hand side of the equation, on the other side of the equation. So in the way how I see it, just think about it this way. We can evaluate, I mean, just right here, I mean, what can we do with an equation like this? And I didn't even get into talking about what a multivariable function is yet. Let's hold on to that, even though it may click for you a little bit already. But we can, with an equation like this, the most natural thing is we can think about evaluate. We can evaluate the value for z. Okay, if let's say we assign x equals 1 and y equals 0, for example. Okay, and so now you have seen how I just wrote these. I did not prepare these values. These are, that's why I so-called, these are the independent variable. So that's why I was saying earlier, take as much understanding as you've had, take as much understanding that you've had from your previous courses about function into the study as much as possible. So back in the old days when we think about function, there's the x here. See, just earlier I called that the input. Now it's also known as the independent variable, because once we are, anytime we're about to give a value for the input variable, we can pick anything we want. It doesn't depend on anything. That's why it's called the independent variable. And so now here in this expression, in the way how I just now came up with these 2 values, x equals 1 and y equals 0, I really did not plan anything ahead. It came out completely out of my own creativity. But that's now I'm telling that in front of the screen right now, it will definitely give you the understanding that these 2 variables right here, the way how I chose values for them, that is completely independent with any restriction. There's no rule about how I can choose an x equals 1, or there's no rule that making me choose y equals 0. So choosing a value for this variable x and choosing a value for this variable y is completely, those are all completely independent. All right, so these 2 are the independence variable. And so now back to the problem that we are in the middle of. Let's evaluate z. If x is given value 1 and y is given value 0. So in that way, now I'm going to move on to the other side of my board right there. So in that way, z, again, in the way how it's set out, in the way how it's set, we already saw there's a rule. So the rule to calculate z, and you can think of that also as a formula. So right now z is simply just a formula or a rule. So the rule says we multiply 3 with the square value for x, okay, plus 4 times the value for y. So now with x equals 1 and y chosen to be 0, again, let me note this. These are independently. All right, independently chosen, those 2 values right there, 1 for x and 1 for y. So now all we do is just, of course, when I'm explaining in front of the camera and in front of everyone learning right here, then I have to go in slow step and explain in details. But it's very natural now that we just simply plug it in. Plug x into x and y into y for our expression. So that means in the next step, z will come out equal, so 3 times the rule of z says we're going to multiply 3 with the square of the value for x. So the value for x is given to be 1. So 3 times 1 square, okay? And then so just be careful with using parentheses. Anytime that we're substituting a value into a variable, then we're going to just put that inside a pair of parentheses. That's all. So now plus, the rule says additionally we need to add with 4 times the value that was given to y variable. Okay, And so now z equals, so as far as the calculation now, z comes out being, so 3 times 1 squared is 3, plus 4 times 0 is 0. So z comes out being 3. So we have a value for z. Now we have obtained a value for z. Z is a variable. Its value can change just like any other variable that you have learned. But now in the way how I'm seeing it, back to what I noted here, these two values, x equals 1 for the x, and y equals 0 for the y, these two values are independently chosen. But the value for z here was not in any way independent at all. The value for z here came out completely dependent on what we chose here for x and y. So now the z here came out according to the rule for that was set up here previously. So here I'm seeing that z is dependent. Okay. And when I say z is dependent, I mean the value that we can calculate for z is dependent. Because now think about it, the same rule. Okay, I just want to point out how dependent z has to be. We can independently choose x equals 0 and y equals 3. Okay, so again, just now I gave you that impression again that we can choose x and y, the values for x and y completely independently. But now z, and now I can pick up the pace right here, z, the same rule that's being highlighted here. Z can be, so now 3 times 0 squared, so 0 substituted for x, plus 4 times 3 substituted for y. The exact same rule. The rule says we multiply the square of x with 3, the square of the input x with 3, plus with the square with the y value with, well, being 3 right now, 4 times the y value. And so now z comes out being 12, okay, because that's a 0 plus 12, and that's a 12. So clearly z is a variable because the value of z changed. See, now this is a different pair of values for x and y right here, and we change, z comes to a different value. So, and this value here calculated completely based on the pair of values that we gave for x and y right here. And so once again, I just show that z is, again, dependent. So all of that idea about independent variables and dependent variables are all here. All right, and I still didn't get into formalizing what a multivariable function is, but you keep getting closer and closer on your own right there about understanding what a multivariable is. Okay, and so see, we choose the values for x and y completely independently. And there's not even a rule that, hey, when you choose x equals 1, you have to choose y equals 0. So these two variables, their values are completely independent in the way how we choose, and they're also independent from each other. There's not necessarily any rule about how we choose the values for these two, as they must relate to each other. They don't have to be like that. All right, and so now let's observe in the way how it is. We're starting out with a rule. A rule. That's the famous thing to know about function. Anytime we hear a rule, that's the idea about a function. Okay, and then, but now in this rule right here, we have, unlike the old days, so now I have to say, unlike the old days where only one input variable responsible for changing the value of your output. So this is input, this is output, but in the old days, up to any point prior to learning about this concept, multivariable function, then that's what I refer to as old days. So in any time prior to this point of learning in this lesson, then any function that we're looking at only take one variable, only take the input for one variable, and only one variable was responsible for coming up with the output right here. Only one variable. Back then, anytime before this point right here, there was only one variable that's responsible, or there was only one independent variable, or there was only one input variable that's responsible for, determining the output value. So that was the old day. But now if we're looking at a little more closely into this new formula or this new rule I'm introducing, it's still a rule. Okay, it's a rule. Let's make a further note right here. It's a rule, making it consistent with the fact that it's a function. Okay, but this rule here has more than one. So now the term that I introduced earlier, multivariable. Okay, multivariable. So I'm a little bit short of space right here, but you see multivariable. Multivariable function. So that prefix multi right there refers to having multiple or many. Okay, anywhere that's more than one. So again, back in the old days, we only needed to work with one input variable, and only one input variable back then was responsible for changing the output values of your function. But now here in our case right here, in this rule over here, it's a function, but now more than one, anywhere more than one. That's why it's multivariable. Okay, more than one variable, more than one input variable. Okay, that's responsible for changing up the value for your output. All right, so now in this case, and so now after investigating about two problems where we substitute different pairs, so also another wording to come out right here, another common terminology right here. So in the way how I've been working through with two different problems so far, two little problems, then this one right here, I refer to that as one pair of values. Okay, because our rule right here require two variables, two input variables to come together and come up with the function's output. So we require two variables here to determine the output. And so the two values here is referred to as one pair of values. And then here we have a different pair. All right, so here is, see, another pair of values. All right. So now this is the idea here. We can, at this point, after investigating about two problems where we come up with different pairs of values, we selected a value independently for x, and we in the meanwhile selected a value independently for y right here. So with a given pair of x and y values right here, we came to different output value for the variable z that we assigned for the variable z right there. So the variable z is dependent. Okay, and it came out to calculate z, to get the value that we assigned for z, we had to follow this rule right here. So z is this rule. We get the value for z by going through this rule. Okay, and this rule takes two input values at a time, two input values. Now, be careful in the way how I'm saying, because I'm preparing that, I'm making this lecture for any audience right here. Doesn't matter if you're going in whichever field that is. So here, even if you go a little more advanced right here, I still see this is as one input. Okay, but it has two values, so one pair is one input. So it's one input, but two input values together as a pair. Okay, and so one pair here as a one input, but then one input exists as a pair right there. So there you go, two inputs values together as one pair, as one pair of inputs responsible for coming up with or determining the output right here. So this is the output. Okay, so in that same way, see, this is one pair right here. Okay, this is one input, and we have only one output. All right, so for each pair, there's only one output right there. So now and for one input, there's only one output, as I've been saying. Either here the input here existing as a pair, the input exists as a pair of values. The input here is a pair of value. Okay. So this is the input. This is an input right here. Okay? Input as a pair, input as one pair, input as another pair of values right there. So one input as a pair come out with one uniquely calculated output. One input come out with one output. So no matter what we do, it's still circulating around that concept of having a function. One input coming out with one output and determine only one output. All right, and so now at this point, Now I can erase this. All right, so now we can formally name that. So now I'm going to say now Z is a multivariable, okay, a multivariable function. All right. So instead of single variable like the old days, now we're looking at Z is a multivariable. It's a multivariable function, and it's a function of x and y, of the pair of values x and y right here. So x and y, x comma y right here is one pair of values. So let's make some clarification right here. So x and y right here is a pair, okay, of a pair of values, okay, and then they're used as one input, okay, to the function. All right, so that's the idea of what a multivariable function is. So two values, two variables at the same time together exist as one pair. Okay, that gives two values together at the same time responsible for determining the output value of your function, and that's what it means by multivariable. And so now at this point right here, and I don't want to get into a formal definition because it's gonna make just our discussion here lengthy, because all of that understanding has already been delivered and you have successfully learned up to this point. So now we're just gonna, on top of what we have learned and become fluent already, we're going to just simply add on with that idea right here. Instead of just one variable responsible for the outputs, now we have multiple variables responsible for the output of our function right there. Okay. All right, so now upon agreeing that Z is now a function, but instead of taking only one variable, so that's Z that I wrote earlier, Z as a variable, but it has a rule. That was a rule to come out with the value for Z right here. It was 3x squared plus 4y. Okay, so now we just now agree as what I wrote, according to what I wrote on the other board, it's a multivariable function. Okay, so now we're starting to work with a multivariable function. We understand what a multivariable function is. It's a function where each input is a pair of values like that. Okay, so at some point here and there I call it interchangeably that it's a pair of it's two input variables, but really it's just one input. Okay, but it has one input as a pair to be precise like that. Okay, so two variables responsible, or two values together as a pair responsible for determining the outputs. And so now it's time to come up with notation. Okay, so let's make a comparison chart right here. Okay, so back in the day, this is the old day right here. So when we're looking at a single variable, okay, then yes, we use the notation f of f in parentheses, and so we assign a rule with a name. So this is function's name, as we already know, a function's name, and then this x right here in a pair of parentheses comes together as one whole package of symbols here. So this entire notation is indicating that we have a function that we name f. Okay, and then in the entire expression of the function, and whenever we see the x variable, that's the variable being the input responsible for coming out with the output. So this was back in the old days, one notation. But now our Z here, now in the new form right here, multivariable. Okay, multivariable. And so now, yes, you can still name your function f. Doesn't even have to be lowercase, f or g or h, just like the old days. But now we want to indicate there's a whole pair of values, a whole pair, or even more than two values, even more than even more than two, if you're working with more than two variables involved in your function, then we can go even more. But for now, in this case specifically, how about two variables, okay? Two variables are responsible for your function, then we're going to indicate as the following. So f takes one pair of value x comma y right here. All right. So x takes one pair of values together. So that way right here is indicating each input is a pair of values, just like how I was saying earlier. It's one pair of values exist together as one input. But sometimes you may hear me using the term two input variables. Yes, as if we're talking about variables, then there are two variables. That's why there were two input variables together, okay, responsible for changing the output of our function. But in the end, two input variables here make up one pair of values. And that one pair of values right there, for short, we can just call that this one pair right here is one input. Okay, take that clearly right there. And so we can call that, just earlier we can say that z equals a function named f that takes two variables x and y as a pair right here. And so now, as we get to as we start working with multivariable, I want anyone learning from the lesson to be a little more careful right here, because back in the old days, the variable we have is the only variable. Okay, and so for that reason, anytime that you see the x, and you know that the x is the one that's responsible for changing the output of your function. But now, here's the thing. Now, when we're working with multivariable, when we're starting to work with more than one variable that's involved in your function, then be careful a little bit in the sense that in the way how the notation is used, then just strictly follow the way how it is right here. Then once it's defined, then the first value in the pair is going to be whatever assigned for the x, and the later on is assigned for the corresponding variable if you recognize that, if you spot that in your rule of the function. Okay, so it's not like once you decide and then, so for example, quick little example, what I mean here is when you see f of 1 comma 5, for example, that's what I meant right there. So now, according to the way it's already, you can call it z comma y or z comma t, but whichever comes first, once you assign actual values right here, then whichever comes first in the pair, for example, is to be substituted for the whichever one that you listed first. All right. So once it's defined like that, then make sure we respect that order. And so it's not so. What I mean now is that this is not the same. It's not the same as f, but taking 5 comma 1, because 5 comma 1 is a different. It still involves two values, 5 and the 1, or the 1 and the 5, but they have different roles. That's the idea. In this right here, 1 is the value for x that we give for x. 5 is the value we give for y. But here, 5 is the value we give for x, and 1 is the value we give for y. So the order of how we write our function notation here does matter. Okay, the order here. And that's why now when you are taking some more, when you get a little more advanced into your mathematical learning, then these pairs of values right here, to be precise, we call them the order pair. Okay, so I can get on this board right here, and back to what I was saying, x and y is a pair of values, right? And we use as one input right here. Now we can even add in a little extra note right here. This order pair right here, to be precise, okay, and you can also, in case you already took note right here, you can also go back right here and add in one extra description right here, that it's not just a pair, it's an order pair, okay, an ordered pair of values again. All right. So x comma y is an ordered pair of values, because once you give that order x first, y, and then comma y, and then maybe later on, if we're working with functions of more than one variable, more than two variables, then it's not a pair any longer. It's a triple. It's a triples, or it's an and tuples or whatever. But it has an order. All right. And so now for the easy case, when we're working with two variables and x and y is an order pair right there. All right, so that's the basic idea about what multivariable function is. So now we are ready for getting into example 1 right here. All right, so in this example, I am going to be looking at a mix, sort of like a mix of different notation used right there. Okay, so how about in example 1 right here? Let's call it. Let's say let's come up with the instruction of the problem. Let's evaluate. Okay, and now we want to come out with. So what do we want to evaluate? So let's say in part A, I want to evaluate f of 1 comma negative 1. Okay, f of 1 comma negative 1 for f of x comma y. So here comes the actual definition of my two variables function right there. Okay, x double variable function. So f of x comma y. So look at this notation carefully. See, I'm in the way how I define it. X is whichever listed first, and y is the one listed after. So that's the order of how I listed my values right there. So now f in parentheses comma y is a function indicating that this function is a multivariable function. It's a function that has two variables involved as one input. So each input has two variables involved, or two input variables involved. So here's the rule over here. The rule for f says we're gonna go x cubed plus 4xy plus y squared. So now that comes the part of the function. I mean the rule of the function, the actual written rule over here. So the rule say whichever we assign for x, we're gonna cube plus 4 times the assigned value for x times the assigned value for y, and plus the assigned value for y square, or the square of the assigned value for y. But in the end, the point now is that, you see, this notation is extremely important, because now you can see that f in parentheses x comma y, so it's an order pair, as I keep yelling out loud. So now that means when you're reading this, because this is what we really are evaluating. So f of 1 comma negative 1, I now must understand. Anyone learning this must understand that. Now this is to substitute for x, okay? Or that's a very awkward way of writing that. How about, so that's just indicate x is assigned to be 1. And then this value right here, the second one in the pair, after the comma, that value is understood as the value for y. That's what it is. All right, and once we have understood that clear enough, now we can proceed easily. The problem can move on easily. So now the rule says we substitute x equals 1, okay, for any of where we see the x variable here. So I'm looking at 1 cubed plus 4 times, so 4 is a coefficient assigned in a function. 4 times 1 for x. So y variable is assigned to be negative 1. So now it's negative 1, okay, plus and negative 1 all square. And so just that, I highly recommend to use parentheses extremely carefully anytime that you're doing a substitution right here, especially now when we're involving more than one variables. Okay, and so now, just in that, we can go ahead and proceed further into the evaluation problem. That gives me a 1, okay, minus 4, because that's second term right here, and then plus positive 1. Okay, so in the end, my final output here is a negative 2. This is the output. Okay, so together, this is, all right, this one pair right here. Okay, this is the input as one pair of value. All right, and then this value here is the output. That's all there is. All right, and so now we are ready for part 2 of the example. The same example 1 right here, but let's look at part 2 right here. All right. And so here, before I really get into an actual next part right here, let's give it an FYT problem right here. Okay, So FYT stands for your own trying right here. So how about with the same function defined here in part A? So let's look at f of minus 2, 1. Okay, so now just in that way, again, just for anyone being new to this, I only need to remind you, this means x equals negative 2 and y equals 1. That's simply it. It's not like 1 is a switch for x and y is switch for negative 2. Nope, it's in that order. So now when we actually see the symbols with the values given right here, then the first number is the x and the second number is the y. That's also the intention of a whole list of variables involved in your input. Okay, but now being an FYT right here, it means you are going to take your own try right there. I won't show the steps anymore, and feel free to pause the video, and once you are ready to resume, I will you will only see me showing the final answer for that. Okay. All right, so after spending some time with that, hopefully, now this means this value here is simply just negative 15. All right, and so this is one pair of inputs. This is one pair of inputs. Okay, one pair of values, and that's one input right here, and it comes out with this is your output right here. All right, and so now after this FYT right here, now we are ready to advance into the next part of the same example, so that we can just keep getting better and better at working with the multivariable function. Okay. All right, so now how about in part B of the example, let's look at how about a function as following. I can call that we want to evaluate some function c at the two value 4, 1. 4, 1. So this function here is called c. It's evaluated at two values here 4, 1. Okay, but now here's the definition of the function right here. So c of so really I'm getting tired of x and y all the time. So how about the u and w? Okay, so two variables here. So that means even before I write the definition of the rule of our function, and you can see that, when we actually proceed into working with that, then that means when we're substituting values in, u equals 4, and this 1 right here is for w equals 1. All right, and so now we really are ready now. So the rule for this function c right here is, how about c equals the u raised to the power of 0.5, okay, times w raised to the power of 0.75. Okay, so it's a multiplication here, and there's powers right here, quite ugly looking powers, but it's completely doable with our majority in math up to this point right here. Okay, so now again back to what I explained. See, this is an order pair of values right here corresponding with u and w. So the first number before the parentheses is here. The first number before the comma here is corresponding to the u variable, or to be substituted for u, and then the second number is for w. All right, so there's a huge difference between c of 4, 1 and c of 1, 4. As far as two numbers, 1 and 4 makes no difference with 4 and 1, but now it's an order pair. All right, and so whoever comes first in a pair, that means it's corresponding to u, and then according to this definition that was given previously. All right, and who comes after the comma, that's corresponding to the second variable. All right, and so now let's go ahead and calculate. So that means c of 4, 1 equals, so as I indicated here, as I noted earlier, then now it's going to be 4 substituted for u, and then we're going to raise to the power of 0.5. All right, and times now 1 substituted for w here, and then in our rule right here, w is raised to the power of 0.75. All right, so now I don't want to keep swinging back and forth between here and I don't want to swing over to my computer to graph a calculator yet. So think about this. 0.5 right here. You can use your calculator, but 0.5 is the same as a square root. So here it's a 4 to the 1/2 power, okay, or a square root of 4 times the 0.75 here is the same as a 3/4, but 3/4 is the same as so that's taking a square root of 4 times the 4th root of 1 cubed. That's what the 1 to the 3/4 is. So these are all still just easy number to calculate, and that's the reason why I didn't want to swing over to grab the calculator at my computer station. So here is simply going to be, that's a 2 times a 1. Final answer here is 2. All right, so now once again, this pair here as a whole pair of value, that's one input. So this is the input as a pair. The input as a pair. And this one here is an output right here. All right, so one pair of values. Okay, one pair of values determine an output. Okay, so each pair requires two values. So that's why one input requires two input variables in each one of the inputs. Yeah. All right, and so let's look at another FYT right out from this function right here. I just want anyone learning with me in this lesson to have a chance to practice on your own right there. Okay. All right, so now how about as an FYT right here, right after working with part B. So FYT here, we're still going to take the same function here. All right, but now let's evaluate C at 1, 16. 1, 16. All right, so go ahead and apply what you have just learned in how I did that in part B right there. And feel free to pause the video to do your own calculation. All right, and so at this point, assuming that you have already spent some time working, the final answer for this FYT right here, and it's an FYT, so I am not going to show how to calculate that. I'll just simply point out the final answer here. This is going to be 8. That's our final answer for that. All right, and this is this is one pair of value. This first value here is corresponding to U. This is corresponding to W. Okay, and then so this is input, okay, and this is output. This value here is the output. All right, and so now let's try another one. Let's look into the next part of the example over here. And so now let's look at part C. So in part C, how about for part C right here, same example 1, but I'm going to depart from the functional notation from the f of x comma y or the c of u comma w. I'm going to depart from the functional notation, but I'm going to use even simpler notation. So simply just this, just like the one I introduced right before we began, right when we began with talking about multivariable function. How about just one simple variable z right here, and z equals to a rule. So the rule here says x squared plus xy over x minus y. All right, so right now, yes, we see z here as one variable and two variable x and y involved together to come out with a value for x right here. Okay, and now we know we let x we want to calculate the value for z according to this rule. That's the idea. If x equals 3 and y equals 2. If x equals 3 and y equals 2. So now when your multivariable function, or here it's a function of the two variables. When your multivariable function is given in this way right here, and without using the functional notation, then we don't have to worry about the order, because it's already specified clearly right here. 3 is the value for x and 2 is the value for y. All right, and so now in that way, I'll just simply substitute in these values right here. So z, to come out with the value for z right here, we go 3 is substituted for x, so 3 squared plus, now 3 times y equal 2. So 3 squared plus 3 times 2 in the numerator. In my denominator, I'm looking at 3 for x minus 2 for y. That's all there is. All right, and now we're ready for a final calculation. The denominator here is simple, it's just a 1. Okay, and then here it's a 9 plus that gives me a 6. So altogether it's a 15 right here. All right, that's my output value. So now if we're seeing, now as we're clear here, we're seeing this as a function. So if this is a function intended to be, then this pair of values right here, this is your input. Okay, and then this is our output. All right, and then same function. How about let's save that same function? We can do an fyt right here. All right. So with this fyt, how about let's look at, we want to evaluate the same thing right here, but when x equals 4 and y equals -1. Okay. All right, so now take your time to do the calculation, and then I will just simply show the final answer. All right, so the final answer here is z equals, so just like back in the problem, 15 here is the z, but seeing z as a function of x comma y, x and y, then this is an output. So now the output for z here is going to be 15, 12 over 5 here. Okay, in irreducible, in the reduced fraction, it's 12 over 5. All right, so now let's get into another part of this particular example. Okay, so now let's look at part D of our current example. So we still want to evaluate, and here I'm looking at, so we want to evaluate, I'm going to call that V, okay, that is equal to e raised to the x plus y power, okay, or e raised to the exponents x plus y. So we have the two variables, the two input variables being placed in the exponential part of our function. Okay, it's being placed in the exponents of our function here, the e to the something. All right, and then now, so we want to evaluate v right here, but and at a given value, how about x equals 1 and y equals 0. So now this is a whole pair of values right here. So right now I see this. This is one pair of value. This is my input right here for that. When x equals 1 and y equals 0. All right, but then in the end, so much explanations about it, but it simply just means we're going to substitute these two values in place of the x and y variable of our expression here, and then that's how the calculation is done. All right, and so that now means my value for v is going to be e raised to the power. So in the exponents part right here, I'm looking at 1 substituted for x, okay, plus 0 substituted for y. So that now gives me e to the 1 plus 0 in the exponents here is just simply 1, so e to the first power, or just e. So this value right here, so I call that pair, the x and y, is the inputs. So now this final value right here is the outputs again. All right, and so again, just to get anyone learning from this lesson here really comfortable with the idea of evaluating a function of a multivariable function, then I'm gonna, in the same problem part D right here, let's look at an FYT right here, where I'm gonna draw the exact same rule. I'm gonna take information right out from that exact same rule. So here we go, the FYT here, we want to evaluate V right here, but at when x equals -1 and y equals 1. When x equals -1 and y equals 1. So go ahead and pause the video, take your time and follow the steps just like how I was doing it in the early part of part D right there. Okay, and then once you resume the video, I will just simply show the final answer. All right, so at this point, I assume that you have already paused the video and spent some time working on that. So I'm just now going to show the final answer without showing the actual steps. Okay, so your final value for V here is going to equal just simply 1. All right, so V equals 1. So here in this FYT problem, this is your input right here. The two values x and y together, that's your input. That's one input, but containing two different values. Okay, and then this is your output. All right. So now we're ready for another one. And I believe this next one here I'm showing is about the last one of this example 1 right there. Okay. All right, so now in part E of our example, let's look at how about V equals, so we want to evaluate V where V is defined as the following rule right here. We take the logarithm, natural log of t squared plus s squared. All right, t squared plus s squared. And then we want to evaluate this given that t equals 1 and s equals 0. Okay, so t equals 1 and s equals 0. So again, as far as the understanding about function, then this entire pair is the input. I mean, the order of this pair shouldn't matter really. Okay, but so t equals 1, we're going to substitute for t in our current function. S equals 0, we're going to substitute that into our current function. All right, and so now in that way, here's how I'm going to find my output right here. V equals, I'm going to fire up a logarithm, a natural log operation. But then inside of the log here, I'm going to have t value, which is substituted by 1. So I'm looking at 1 squared plus, and so now s squared, but s is substituted by 0. So here we're looking at 0 squared. Okay, and so that now gives me, in the next step for the calculation, this is natural log of the inside. Now, it's the way how it is. We work from the inside out right here. So for anyone arriving at this lesson, your algebra should be solid enough for you to be aware that we're working from the inside out when we're working with a logarithm. Okay, and so 1 plus 0 is a 1. So this problem here looking big at first, but now reduces down to natural log of 1. Okay, and now we learn the logarithm of a 1, and doesn't matter what, regardless of whatever base that is. The logarithm of a 1 equals 0. All right, so now this is going to be in a box right here where I see this as my output. So this is the value that we have determined, that we have evaluated for V right there. Okay, so this is output. Okay, and then the two values here is input. And so let's do an FYT again. Okay, so now as far as an FYT, the same function here, V. All right, so now let's look at an FYT where we're looking at t equals -1 and s equals 2. Okay, t equals -1 and s equals 2. All right, so go ahead and pause the video, spend some time working on that, and follow exactly the work how I've done here. And just think about that. This is just a different inputs we're giving to the same function. A different input we're giving to the same function. All right. And so now at this point, assuming you have already spent some time pausing the video and now you're ready to advance, I'm only going to give the final answer to this. All right. So V here is going to equal natural log of 5. All right. And I don't have a calculator with me immediately here at the computer station here, so I'm just going to leave that this final answer in exact expression like this, natural log of 5, and you can always verify me with that. But this is the output right here. Okay, this is the output, and this pair of values right here is the inputs. All right, so at this point we are at the end of example 1, and my intention, and you can see that in my style as I walk through example 1 here with anyone viewing the lesson here, then after each problem, part A, part B, part C, after each problem where the function is still there before erasing it, I put in an FYT right there. So say part A, I gave you a function, I worked through one problem with a given input, and then I ask you to use the same function there with a different output. Okay, so that you have your work and my work and your work and my work right there. But so the point now is that, see, on each of the problem, each problem of example 1, we're looking at, the 2 different inputs and responsible for different outputs right there. So that once again, I want to emphasize that these are all functions, multivariable functions, in a sense that, see, I can work out and work through on each given function right here. I can give out one input and go through my work right here and come out with some outputs. And then your FYT problem right there, think of that as a different inputs we're given, as a different inputs that we're given to the function. And then, see, 2 values will come, the point is 2 values together will be just enough to change the output right here. So in this function, same function, that's my work and your FYT work right there, but a different input right here gave me a 0 for output, and a different input here, -1 for t, 2 for s, as a pair of it. That's one input, it gives you a different output right there. And that's how it keeps enforcing that these are all multivariable functions. But so anytime you want to change the value or come up with a new output value, we need all of the input variables values present there in order to come out with the output. All right. All right. So the entire example 1 so far has shown you all of those functions. Has given the students who learn from this lesson enough experience with when those multivariable functions contain exactly 2 variables. But now back to the term right there, multivariable function. Okay, the idea now is that we're working with any of those what so-called multivariable, functions. So being multivariable, and I specifically just need to underline that prefix multi. It just means many, anywhere more than one. Okay, it just means many, anywhere more than one. And then just now throughout example 1, we get ourselves comfortable to evaluate those functions of 2 variables, those double variables functions. So that's one example of multivariable functions already. But now that means as long as we can work with functions of 2 variables, then why limit ourselves to only functions of 2 variables? There are now functions of 3 variables existing out there. There are functions of 4 variables existing out there. Okay, and so now let me swing to my other board right there. So back on this little chart right here, see? So now specifically in the old days where functions that we worked through the whole time before this point right here is function of one single variable, then it's f of x right there. And just now we've looked at the functions of, well, we're starting to get into multivariable function. And then we started out learning about function with 2 variables. And so notationally, we use f and then an order pair right here with some indicated meaning that once it's written like this, then that means the first number given in the input has to be is designated for the x, and then the next one here is designated for the y, whatever we call however we name our variables. Okay, and so that's how we come up with the notation for 2 variables function or functions of 2 variables. And so I'm still going to retain that, but I'm going to erase this part right here because this is 2 variable. So what about 3 variables or more? Okay, so the same chart right here, I'm going to produce one more row. So we can write f of function's name, and just like that, we can have f of x, comma y, and comma z. And indeed, I shouldn't, if I name z here as my input, then I should have used w here, for example. Okay, so w is the variable that we name for the output, and the output here is determined by the rule that we name f. Okay, and this rule f right here takes 3 variables. So this is now, instead of a pair of values, this is like what I was saying earlier. We have here a triplets, okay, a triplets of values like that. Okay, a triple, the 3 values together. Okay, a triple of values. Okay, and then it's an order triplets. And then, so this is 3 variables. And so now we can even have even more variables. So in a more general case right here, we can have up to n variables. All right, so our function is going to look as following: x times y, x comma y comma z comma t comma s, as many as possible. Okay, but a lot of times, most of the time, we're just working with 2 variables and 3 variables and 4 variables and more. We're just going to keep those as some theoretical ideas existing out there, but it's not directly relevant to our daily work that much. Unless anyone after these lessons will advance to a real advanced courses in math, and that's where you're going to work with much more, functions of a lot more variables, starting with 4 and more. Okay, all right, so in that way, now I just point out, if we can have functions of 2 variables, that begins our understanding that we can also have function of 3 variables or even more. Okay, so now in the later examples here, okay, and which I'm about to give, then no one should be shocked that some function we have 3 variables, some function we have only 2 variables, and it's just a mix of, because these are all in the end multivariable functions. Okay, and then these are either a pair or a triplet of values right here. Those are just in a certain order. Okay, so now let's look at our example 2 right here to get real comfortable with that. So example 2 really is intended to be very similar to example 1 that we've done earlier. We just want to get comfortable with evaluating. So how about let's designate example 2 here for those functions of 3 variables or even more. Okay, because we dedicated the entire example 1 for functions of 2 variables. So now let's get comfortable with functions of 3 variables or even more. Okay, so we want to evaluate in part A f of 1 comma 2. Okay, so some functions f of 3 variables, and then there's a value 1 for the whatever the first, we call it the first variable, and then the second variable is also 1 and 2. But now I have to write in the actual definition. So f of x, y, and z, and that's why this is now important right here. So now with this notation right here, it's indicating that our first value here is corresponding to the x. The next value in our triplets here is corresponding to the y, and the last one here is corresponding to the z variable. And so I'm expecting that the function I'm about to write down is going to have 3 variables present in there: x, y, and z. Okay, so here we go: x times e to the yz. All right, 3 variables present. E is a constant, so that doesn't count. It's a letter still, but it's just a constant. Okay, so now f of 1 comma 2 comma 3. 1 comma 1 comma 2. So now evaluating this, f of 1 comma 1 comma 2, x equals 1. Let's label that. That means this here is indicating x equals 1, because the first one in the triplets right there, is corresponding to the x variable. The middle one in the triplets is 1, and then the last one here is equivalent to z equals 2. All right. So now with the functions previously defined here, so now when we know that x is given to be equal 1, then here it's 1 times, now in products with e, but in the exponents part of this function here, I'm looking at, so 1 substituted for y, and then 2 substituted for z. All right, and so now with the order of operation that kicks in right there, then now I'm looking at e to the, because 1 times with anything is just that quantity, so I can now skip the 1 there. 1 times 2 is 2, so e squared is my final answer right here. And then so without having a calculator right now, I'm leaving this final answer here, this final output here in exact expression. But if you have a calculator, you can go ahead and obtain your own numerical value for that in decimals. Okay, but see, so now what I have here, this is outputs. All right, this is output. So 3 values involved together, 3 input variables involved, but in the end, all of these 3, the whole triplets is, this is right here, the whole triplets is your input. Okay, so we give 1 input right here, being 1 for x, 1 for y, and 2 for z. Your function has 3 variables, we named that x, y, and z right there. All right. So still in part A right here, same function. That's basically what I want to retain right here. Let's calculate, let's evaluate the same function here at a different input right here. And I'm writing that down as an FYT for anyone to try. Okay. All right. So now as an FYT, so why don't we try f of 1, 0, 1, 1, 0, 1. All right, so this is an FYT, and all I need to remind you. So in this way, this FYT still takes the function defined right here. Okay, so this is equivalent to x equals 1. That means it's indicating that x equals 1, y equals 0, and z equals 1. All right, and now you can go ahead and pause the video and spend your own time working on that a little bit. Okay, and then I'll just, once you resume, I'll just give out the final answer, that's all. Okay. All right, so now assuming you have already spent some time on that, the answer here, without showing any explanation or steps here, the answer is just simply 1. All right, and so now this here is input, a different input. So, and this is now output. So you have seen earlier on the same function, I was using the pair 1, 1, 2. It gave me an output being e squared. And now with a different inputs, this is, like I said again, the whole triplets here. Okay, so when it was 2 variables and it's a pair, now it's a triplet. Okay, the whole triplets here is a different input, another input versus the one we have done earlier. And so 3 values together in order to change the output. So earlier the output was e squared, now the output is changed to 1. Okay, so now that's the whole idea of multivariable function. We need more than 1 input variable values, okay, in order to cause different outputs, to determine different outputs of our function. Okay, all right, and so now let's look at another problem. All right, so now in part B of the example, how about let's evaluate g. So now I'm going to name that. I'm really getting tired of the naming my function f and f and f all the time. So g, how's that? Okay, so g of 2, 1, 1. Okay, so some function of 3 variables like that. Okay, and then but then let's come to the actual definition of our function here. Let's see what g is defined as. So how about g here of x, y, and z, 3 variables. It's a triplet right here. And how about that is x squared y plus z cubed. X squared y plus z cubed. X squared times y plus z cubed. All right, so now according to the way how this triplet is defined is ordered. According to the way how this triplet is ordered, the first number is indicated to be the x, the next one is the y, the last one is the z. So that means in my expression right here, in my notation right here, it means that this is x equals 2. We're going to substitute 2 for x in the function. Okay, and then we're going to substitute y equals 1 for y, okay, into the function. And then we're going to substitute 1 for z in the function. So this is together as a whole triplets. Input, this is 1 input. All right, and so now that means f of 2, 1, 1 equals 2. Now x squared, but x is substituted by 2, so 2 all squared times y equals 1. So now it's times 1 plus, now z is cubed, so plus z cubed, but z is substituted by 1 again, so plus 1 cubed. All right, final answer here, and it's now just a very simple calculation. So final answer out of this calculation comes out to be 5. Okay, that's what I call, this is here, output. But see, in order to determine an output, and that's ideas throughout the whole discussion so far from the beginning. Okay, but in order to determine an output of a multivariable function, we need multiple input values to come together. Okay, so just simply indicating x equals 2 and leave the rest is not going to come up with an output yet. All right, so that's the idea right there. And so now again, let's look at some FYT problem. All right, so here we go with our FYT right now. Okay, let's evaluate g of 2, 1, 0. And on the same function, x squared y plus the z cubed right here. So again, just a little hint for anyone watching this video. This just means we substitute 2 for x, we're substituting 1 for y, and we're substituting 0 for z right there. That's all. All right, and so go ahead and pause the video, spend some time to work on that, and spend as much time as you need. Okay, and then once you resume, I'm just gonna tell the final answer to that. All right, so now at this point, hopefully you've had enough time spent on the problem right here. The final answer will come out, and this is being an FYT, so I'm not gonna point out the reasoning for that. All right, so the final answer here is simply just 4. All right, so again, the whole triplet here is a different input compared to the one that I did on the same function. But here we're looking at, think of that as, if you put your work together with my work earlier, see, we got this on the same function. I tried one input, and you worked on a different input. Okay, and then, but anytime we're looking at one input for a function like this, it's got to be 3 values coming together in order to determine an output. So 4 here is, again, an output. That's what it is. All right, so let's try another one. And this next one here should be the last one in our example 2, because once you've been through with example 1 right there, then the idea, you have learned most of the idea already. Okay, so there's no need to bring in too many problems in this example 2 right here, because it's just the exact repeated idea, but we're working with more variables right there. Just more variables, more values responsible for determining the output of our function. Okay. All right, so now in part C of our example. All right, so I'm just gonna write down, we want to evaluate w to equal, how about a natural log of x plus y, but divided by z plus 1. All right. So we want to evaluate this expression, and the final outcome is assigned, will be represented by the w variable. So it's a function, okay? But now, in order to evaluate that, we need to have a given value for x, y, and z right here. So x here is 2, y is given to be -1, and z equals 1. Okay, so those are the values we're given. So this is a whole triplets again. Okay, the order doesn't matter in this case because we're not really using functional notation. All right, but now it's simple enough. We can see that it's just a matter of substituting in these 3 different values: x for x, y for y, and z for z. Okay, so now w equals, now I'm going to take the natural log of, so here x equals 2, okay, plus, and y is -1, substitute it for y, and then I'm dividing that by, so in the denominator it's 1 plus 1. That's the exact formula, but I substituted the different numerical answers, the numerical values that we gave for x, y, and z. That's all there is. All right, and so now in that way, my final answer here. Well, how about one more step before the final answer? So the expression on top here is giving me natural log of 1. because 2 plus negative 1 is 1. And then I'm dividing that by 2. But hey, wait a minute, natural log of 1, logarithm doesn't matter any base, but logarithm of 1 will always equal 0, and 0 over 2 is 0. So this is now our final determined output right here. We have determined for ourselves an output on this function. Okay, so these three together is our input. Okay, and we have determined the output for this particular function. That's how it works. All right, and so now again another FYT right here, and I don't think I need to erase the board. I can just still leave it here, and I have enough space here. So as an FYT, same function. Okay, but let's evaluate that when x equals negative 1, y equals 2, and z equals 2. All right, so go ahead and pause the video, spend your time, spend as much time as you can, as you would like to, okay, to work it out, okay, and because once you resume the video, I will only show the final answer. Okay, so now the final answer here is going to be 0. Okay, this is awesome. So I see this as an output. Okay, and all that here is an input. All right, all that there is an input. And so this function, now for this function, I mean the function itself is not special, but it brought up something that just like the day we learned about function of single variable, then sometimes multiple inputs can come out with the same outputs. And this is the case here. The input that I worked through, that I show in front of the camera, I show the steps, is here, and that's the reason why I'm still leaving the work here. So with this, the inputs being different with that input right there, this is a different triplets with that triplets I have here that I worked. So the triplets in your FYT problem is 1, 2, and 2. 1 for x, I mean negative 1 for x, 2 for y, and 2 for z. Okay, but the input I have here is 2 for x, negative 1 for y, and 1 for z. It's completely different, two different triplets right there. Okay, so two different inputs, but they both came out with the output 0. Okay, so just like that, you know, back in the days we were doing functions of one variable. It's entirely okay that we have multiple inputs that arrive at the same height of our function. So here is a similar idea. Now, here we don't have to emphasize on graphing we don't have to emphasize in this lecture here. We don't have to emphasize on creating the graph for a multivariable function yet. Okay, because I want to save that for a separate video lesson right there, where it needs to take an entire different level of attention. All right, so that's how we've done right here, and get students comfortable with evaluating a multivariable function. Okay. All right, and so at this point right here, let's talk a little bit about why do we bother learning about the multivariable functions. Okay, so really it's not about why, but now how about allow me to point out, and then you will find out why we learn about multivariable functions. They have been existing throughout your, all those times in your daily life. They've been existing throughout all those times in your daily life. Simplest example is here. Anyone learning in this video lesson knows how to find the area of a rectangle, a rectangular field, a rectangular room, the room that I'm sitting in right now. Anyone learning in this lesson know by heart the formula to calculate the area of a floor, a rectangular floor, a rectangular shape. Okay, a rectangular shape. Okay, an area means how much filling in. Okay, so we can call that length and width. So now as far as being a rectangular shape, then we can adjust the length longer and make the width a little shorter, or we can make the length a little shorter and lengthen out the width here a little bit. So length and width can always be variables because we can change these quantities. But in the end, how do we find the area of a, think about how do we find the area of a rectangular shape like this, okay, or a rectangular yard, or a rectangular floor of the room, or a rectangular, and so it doesn't really have to be, for anyone being is specialized in math. Any application field deals with area of a rectangular shape sometimes here and there. Okay, and if you're a farmer, you want to be looking at calculating how much area you can do agriculture. Okay, that's the area of a rectangular shape right here. So area generally of a rectangular shape, length times width. We've been saying this by heart since a very young age right here, and we carry that understanding all the way until now. But now as we're looking into this a little more closely, we have realized, wait a minute, this is a function I can treat out. So the product of length times width together, where we have here two variables. So taking the product here, we come out with an output. All right, so I can see A here, area here as a function, L comma W, okay? Being, as the rule here, length times width. Now I just point out functions of multivariable functions have been existing in our daily lives throughout all that time. Now it's just time to bring it out to light and start getting comfortable to it. Start knowing that the existence of these functions in our daily life. All right, so this is one example that's really so close to anyone in your daily life. And so how about another one right here? So yeah, functions of two variables. So what about function of three variables? Do we really see one in our daily life? Okay, so now allow me to bring in another one right here. So just now I was showing how to calculate, calculating just that formula to calculate the area of a rectangular room. The area of the floor of a rectangular room is that area equals length times width. And so think about the room itself that I'm standing in here has a space. So a rectangular shaped room has a space. Okay, so how much space is this totally filled in here? How much volume that's filling in the entire space here? So the room here has some length W, it has some width it has some length L, it has some width W, and it has some height. The height of the room I'm standing in right now. Okay, and there's a length of the room and there's a width of the room. But how much volume, how much space I have to stand here. So now I call that as a volume. Okay, and so again, we learned about this formula since a very young age, and now it's all here for us. And now this is how we put our major thought into it. Okay, our major understanding into this. Length times width times height. This is the formula for volume of a rectangular shape, a rectangular box, like a cereal box. Okay, a rectangular room, like the room I'm standing in right now. Okay, or the volume of a rectangular, whatever, like a textbook that you're using technically has a length, a width, and a depth like that. Okay, it's all this formula. Okay, so this is now in a way how I'm seeing it with our major understanding, the concept of function of three variables, or the multivariable function. And I see volume now can be regarded as a function V. I can also name right there, I can take that name of the variable there as a function's name. And then here this function takes variables length, width, and height being three variables as a triplets. Okay, and then the rule for that, W times L times H. We have a function of three variables. This function has been existing in our lives throughout all that time until now. We just simply realized its existence. All right, so that's how we it's time when you have learned math and become mature enough in math. Now it's time to look at the multivariable functions like that. Again, the idea now is that to calculate the volume of a room like that, how much space in a room, we cannot only provide. I cannot simply just provide any one of you the length of the room and expect you to calculate the volume of the whole room. It's not going to work. Okay, so in order to calculate this function's output, we need to have all three values provided. Okay, so we need to have the whole triplets given. That's the idea. So we need multiple input variable values involved in order to determine the final output. That's the whole idea so far throughout this entire lecture. All right. All right, and so now for any one of my students or for any one of my calculus students who are on track to business fields, okay, on track to business fields, then allow me to bring in a couple applications that live right in your daily work right there. Okay, so in the concept of business, in the business concept, I just want to point out how multivariable functions exist right in your daily work right here. So when functions were still one single variable, we have already studied, and I'm sure you have learned this prior to this point right here, but cost, okay? So prior to this point, you've been learning that cost is a function that usually depending on x here is the number of units, okay? Or the quantity, the number of units. So that's what we've been learning prior to this point. Okay, we're not going to repeat that. So now, where do I see in our daily business concepts like that, where do I see costs that need to involve multiple variables? How about joint cost? All right, the concept of joint cost. I mean, think about it this way. You have your own company, okay? You have this company right here. Your company has 2 factories. Okay. Your company producing whatever the product that is has 2 factories. And that's just a simple case. I'm bringing in 2 factories. Okay. And then so there's a factory X. One of the 2 factories, I call that factory X. Okay, factory X produces X units. So the X right here is in lowercase, where this is the name of our factory. And so of course, in order for factory X right here to produce X units, there's a cost that separately came out. There's a cost that came out from this. Okay. And then, of course, there's the other factory. It takes some cost too. How about the factory Y right there? Factory Y, in the meanwhile, can also produces. I mean, factory Y, on the other hand, produces Y units, where the number of units here I use a lowercase letter y. Okay. So joint cost here means because the 2 factories here are all yours. They all belong to the properties. They're all properties of your company. Okay, and so now the total cost is what I call the joint cost right there. Okay, the total cost, now it makes sense. And right now everything is quite abstract right there. Okay, the total cost can be just simply a function of 2 variables, x and y, where this is the total cost, where how much cost brought in from X company and how much cost brought in from Y company. Now it's not simply somebody can argue that it's the cost from the X company added with the cost from the Y company. Sure, that's one way, but I'm only saying it's one way. Just simply a relationship by adding like this is not always how it works in reality. That's why we, at this point right here, to come up precisely with the function determining the joint cost from the 2 factories or multiple factories of your company, then you need to hire analysts. So that, or at least hire multiple analysts, one from factory factory X, one from factory Y, and then they work together and they blend data together so that they can come up with your joint cost function. But see, this is a function, the cost function that is dependent on the units produced by the X factory and also the units that the number of units that produced by the Y factory right here. But we definitely need to have to know the values for X and Y in order to determine the final joint cost right there, the cost that come from both factories of your company. And this is not the only case, okay? So here I'm just putting in this is just one scenario over here. Just one scenario about joint cost right here. Your company has 2 factories, okay? We can think of another scenario, and I'm still talking about joint cost right there, okay? So we can talk about, how about just one same company? How about your company here produces, or your company is making 2 different products. Okay, there you go. So it doesn't have to be different factories, just 2 different products. A lot of times that's the way how it is. A lot of times for some company. I mean, they of course then as a business strategy, then of course even though it's 2 different products, but they have to create those products in a way that they utilize the same kind of material. So for example, like it's a toy company, for example. They can make bunnies, stuffed bunnies, and stuffed giraffes. 2 different products, but same material. Okay? But it's already 2 different products. There you go. So your companies, think about that scenario. Your company is making 2 different products right there, where X is one of them and Y, capital X and capital Y. So now I'm going to say the lowercase x is the number of units of product X right there. Okay, and then the lowercase variable y is the number of units of the product Y. Okay, this could be stuffed bunnies, and this is stuffed giraffes. 2 different products right there. And so X is in the number of stuffed bunnies that your company made, and then this is stuffed giraffes that your company made, that is making. Okay, and so yes, you can also determine the total cost or the joint cost right here as a function that depends on these 2 variables. How many stuffed bunnies that your company made, right? Okay, and together, as well as together with how many stuffed giraffes that your company made right there, product X and product Y right there. That's how it's done. And so cost as a function, but dependent on 2 or even more variables. That's the concept right there that exists right in your daily work right there for any of those who are planning to head out for business major and business professions. Okay, and so right there in that way right here, right after bringing up this quick application, allow me to show you one example, see how we can work with that. Okay. All right, so to continue with the example number from the earlier one, let's now call that example 3 right here. We are now at example 3. But now as soon as writing down the label of the example, I'm going to swing over and put in the actual worded instruction of the example on the computer screen right there. Okay. All right, so here we go. Here's the worded description of our example 3 right here. So now there's that term I'm using. So if the joint cost, okay, if the joint cost as a function for 2 products is C of x comma y equals x squared plus 8xy plus y cubed plus 50. So here basically just think about, we already have the joint cost function given to us. It's somebody else's job to derive this function, and now we're just going to take that function and do the work on that. So the x here represents the quantity of the product x. It could be like I'm talking about, like what I was talking about earlier about x can be the number of bunnies, of stuffed bunnies, and y here is the number of stuffed giraffes. All right. So X represents the quantity of product X, and Y represents the quantity of product Y. Okay, and now I'm going to undo the highlight just to simply stay highlighted with that with the function. That's all it needs. So now after the description, this question is asking find the joint cost when 200 units of product X. Okay. So what we're given here, 200 units of product X and 150 units of product Y are produced. So now that means back on my board, the function is simply given C of X comma Y equals and now X squared plus 8XY plus Y cubed plus 50. And so now from the reading that we have extracted, from what we have extracted from the reading of the problem right here, we want to find a joint cost. That means we want to find the output value for C right here. But when 200 units of product X, so this highlighted information means when X equals 200. That's it. Okay, and then Y equals 150 according to the description, because you see 150 of units of product Y and 200 units of product X. Okay, this could be, X could be again like bunnies, right? Stuffed bunnies, or this is stuffed giraffes right there. For that company is making toys. All right, and so once we've had these values given, finding the joint cost at these two given separate units numbers right here, that means we're looking at the function C at 200 comma C of this pair of values right here, 200 comma 150. That's how it's done. Okay, so this is the notation, but then really into the work, 200 substituted for X square plus 8 times 200 times 150 for Y, okay, plus, and now this is 150 cubed plus another 50. All right, that's what it is. Okay, and so now that's what that cost right there, and of course, I already mentioned this, and let me mention that again just a little bit, one more time right here, but it's not our concern right now to worry about how this function came around. We just pretend that we're going to be the second stage analyst, that, hey, somebody already derived the function for us. We're going to take that function and do the evaluation right here, okay, to make prediction that, hey, how much cost the company or your company is going to have to spend when we're at that production level, two separate production levels right here. That's the idea, okay? And so now, after successfully substituting in the two values, I'm going to swing over to my computer here to do a calculation. All right, so now after grabbing a final answer here, this final output comes out being, so it's a big value, but it makes sense for a large-scale company right here. The cost here is $3,655,050. That's the cost for producing, one same company, but producing 200 of the X product and 150 of the Y product right there. All right, so that's one example directly relevant to the students who are on track for business applications out there or business fields out there. Okay, so allow me to bring in another business concept right there for those who are taking this class but aiming at heading out for business applications or business fields out there. Okay. All right, so now this is not only just for business field students, and this is really for this problem, this application I'm about to bring in is really for anyone who's thinking or who's having some serious intention for doing an investment. Okay, then we're gonna, when you're doing some research about how investments work, the idea is you're gonna bring an amount of money, okay, into a bank, okay, and so and we're gonna leave that there for the bank. The idea now is that the bank is going to use that money right there for their own business, and then over time they're going to pay you, and that's where we have the concept, so-called the interest. Okay, and so interest is what the bank is paying you for, lending them your money right there. And of course, I'm talking about the kind of money where we don't have a direct use for that at the moment. So we're thinking about making some investments for that, making something useful out of that amount of money to make it grow. All right. And so very commonly now, so for anyone who have some ideas about investments, then just think about, see, the amount I'm talking about that we bring into the bank right there, that's called the principal, okay? The principal value. We have a principal value P. We bring that amount into the bank, leave it there for them. They're going to agree with us. Both sides, both parties going to have to sign a contract right here. The bank is going to say, hey, we offer you an annual interest rate right here, such and such. Okay, so there's that concept. The rate is indicating how fast your money is growing, how quickly your money is growing, or in other words, how much they pay you as a rate yearly by default. Okay, so there's interest rate. Okay, there's interest rate right here, and normally it's written in R percentages. But really, there's when we're doing the actual calculation, then there's always we're using the value K being R divided by 100. Because into the actual work, we divide the number written here by 100. I mean, that's the way how we write percentages. The percentages, like 7%, and here it's going to be the actual rate, there is a 0.07. That's what I meant right there. Okay, so I'm putting anyone into that scenario. And then, so there's the annual interest rate right there. And then so now time is going to be basically how long you want to leave your money with the bank. Okay, so T here is a time variable. Okay, and then this concept here allow me to just mention it, but assume that you have already learned the concept here from a course prior to this. But the interest here is going to be calculated or compounded. The interest is compounded continuously. All right, and allow me to leave the real thorough explanation of this for an econ professor, for a formal business professor to explain what it means by, you know, the interest is compounded continuously. But now, under this scenario, with these, with a few of these factors described here, then anyone on your way learning to become a business professional, then, or anyone who has been doing some research about investment, then under this plan that you are compounding your interest continuously, and with the time right here, and when I'm saying time variable, I mean how long it takes right there. Okay, how long you leave the money in the bank for. Okay, how long it is. Then we come up with the idea of what's so-called a future value. So future value is the principal value times e to the kt. And that k I have defined here previously. K is just basically your rate, but written in decimals. That's what the k is. So f here is the future value. Okay, so now I'm just bringing in a formula that's very well familiar for anyone in business major right there, or for anyone who's heading for the business field that has already had some courses that taught you about this concept right here, the concept where you're finding future value of your investments, where the interest is compounded continuously. Okay. And I'm quite sure that prior to entering this course, you have done this quite a few times. But normally, again, I'm saying normally, we're working in the assumption that we have a rate where it's fixed. Because it's then in the end, just think about you go to only just one bank and you bring in one amount of money. And so you go to one bank, and so the bank gives you a fixed rate, so it's K and T. So the only variable you have been working with any time prior to this class right here is just the T variable. So far prior to this point, you can use this formula as a function, as a future value function in terms of T, the time. So how long it takes? decides how long you leave the money in the investments, decides how big your money is, your future value is going to be. But now think about it. In this in what I'm about to bring in, just think about it. This is a general rule that you go to Bank of America, you go to Citibank, you go to US Bank, they're all going to offer a similar rule. They are going to offer, actually not just similar, they are going to offer the same rule as long as the plan here is compounded continuously. Okay? But why am I saying this? Because maybe you bring 2,000 into the US Bank, but you bring 4,000 principal value into the Bank of America because they have different rates. So my point now is that generally speaking, the whole formula here, it's a ladder. We can change that principal value as well. We can change the rate here, can also change. The K value here can also change depending on different banks. Okay, and then how much time, you know, when you go to Bank of America, you decide that the term of your investment is 5 years. You go to US Bank, your term there is 10 years. So in the end, my point now is that all of a sudden we realize this is really a function of 1, 2, and 3 variables together, right there. Okay, so now in that concept, I can see that future value can be regarded as a function of 3 variables. Principal value can be changed. Interest rates can be determined by, you know, the different banks like that. So that's why in the whole concept right here, it's an independent variable. P can also be independent because you have your control over that. Okay, and then T is the time. It's also for this function right here, it's an independent variable. Okay, and so that means future value can simply be a function P times e to the kt. I mean, I'm just repeating that exact formula here, but now we're seeing that as a function of 3 variables. A function of 3 variables. All right, it's just a general, I mean, it's an application that really exists for anyone who has some serious intention about doing some investment for your life, for whatever purpose that you are planning for. You can become a parent, thinking about doing investment for your kids. You go to college. If you're younger than the age of being a parent, you may be in a situation that you want to save up for, you know, for moving out to a formal university where you have to live in dorms and all that. Okay. Or you think about planning for making an investment for, you know, the day when you graduate and you're gonna go get married and you have enough money to afford your own marriage or your own wedding party, your wedding ceremony. Okay, so there are a lot of scenarios, a lot of situations where you need to think seriously about doing some investments. And so deep behind the concepts, investment is a function, future value, how much your investment will bring to you. That's called future value. Future value can simply be a function of 3 variables. The principal value, the rate offered by the bank, and the term, the time of your investment. Okay. All right. So in that way, after this scenario, I brought it in just to show another useful application of you know, multivariable function. Let me now bring in another example right there. Okay. All right. So here we are at example 4 right here. And again, just like the earlier one, I am now going to swing over to the computer station right there and bring in the wording of the instruction. I mean the worded instruction of the problem right there. Okay. All right, so here we go. Let's spend some time reading the worded description of our problem. So most of the description here is exactly what I was writing on the board right here. And so we can spend some time reading it over one more time right here. So the future value F of an investment earning R% per year, compounded continuously, is a function of the principal value P and the length of time that the principal value has been invested, and also in terms of the K value right here. So, and I should have had that the line described in here as well. But the function, it is given by F of P, comma K, comma T right here, and that equals P times e to the kt, where just like what I wrote on the board, K is R over 100. So this is the function that we have seen on the board earlier. Okay, so so right from that understanding, the question now is find the future value of future value in 4 years. So this means t equals 4 for us. If a principal value of 5,000, okay, is invested as an interest rate of 6% per year, so R equals 6, okay, and that plan is compounded continuously. So we gotta understand that compounded continuously is what led to having this function. And so now once we know that we're in that plan, our function is of course going to be this function of 3 variables, the p, the k, and the t. Okay, so now back on the board. So we know clearly that this investment here gives us the following function. Future value as a function of principal value, and the k right here and the t right here. Okay, it's going to be p times e to the kt. All right, and then so now according to what I highlighted earlier, right here in my highlighted, okay, so we know t equals 4 because we want to find a future value in 4 years if a principal value of 5,000 is invested and the interest rate is 6% per year. All right, so that means we're looking at t equals 4 right from the description of the problem, and then principal amount right here, or principal value here, is $5,000 because that's what it said. A principal value of $5,000 is invested, okay, and then the interest rate here, it's a little abstract, but we have R equals 6%. Right, R equals 6%, but that means K equals 0.06 because 6 divided by, because this is 6 divided by 100. That's what K is. So it's just K is basically just a different way of writing your interest rates, because a lot of time interest rate is, when it's in the written form, then it's written in that number right here with the percentage sign. But then when we're actually calculating it, we have to put it in decimal. That's why I'm using K. Okay? But that now means your function here, and notice E is a known base value. It's 2.718 or whatever longer. Okay? And so now that means, and finding the future value with these requirements. So that means we're looking at, according to this problem, we want to calculate, we want to compute, and we want to evaluate F at 5,000. That's the value for P. Okay? Comma. K is a 0.06 right here. So now it's 0.06, and comma T is being 4 years. That's enough for the setting up right there. And now I'm going to substitute all of that information into my problem. Okay, so now how about I'm going to use the next space in the bottom part of the board right here. So now it's going to be 5,000 substituted for P, multiply with E to the, so now 0.06 is the value for K, and 4 is the value for T right there. Now we are ready for getting a final value right there. Okay, so now keep in mind again, this is the principal value. That means how much we initially brought into the bank. And so now after the calculation here, that's telling us how much it will grow into, That's why it's called future value. Okay, how much our money will grow into in 4 years. If this truly is a plan that the bank is giving us, is offering to us. Okay. And for this problem, allow me to also show my calculation with the TI calculator on the screen right here, but no one is required to use the exact same model here. Okay, and so now for my function, so 5,000 is a value for P. So 5,000 times, and now I'm going to go, if you happen to use the same calculator with me, then it's going to be second ln to access e to the x function right here. And so now we're looking at e. Now in the exponents part right here, I'm looking at 0.06, and I should have had that in parentheses, but it's okay. And then times 4, that's a year right there. All right, and so now this is the final answer right here. So this is how much our money will grow. The money will grow from $5,000 to $6,356.25 in 2 decimal places. All right. And so now that is our final value right there. Okay, so money has grown. Money has grown. It came out being $6,356.25. Another quarter. Okay, this is how much our money will grow into in 4 years. But in the end, the concept we've learned here is that this is, as far as seeing this problem as an application of a multivariable function, then all of these three values together, this is our input right here. So allow me to tackle down right there. This is your input. This is our input of the problem. Okay, and this one here is the output. Okay, so we need three values together in order to be able to determine the final output, the final outcome of a multivariable function. All right.